So rejected titles I had for this talk were 7 things you can keep from the NSA, you won't believe number 4, and I can't believe what this panda bear is doing from the NSA. So this is a really clickbaity title, and it worked, you came. But yeah, can we really keep secrets? Well, we'll see what we can do over the course of our talk here. This is me. I have this really hard to pronounce Twitter handle, and it's even harder to remember, so just go to jamesralexander.com and you can find all my stuff there. The slides are already available. I have a bit.ly link here, and I have a crypto challenge. So this is intended for you to, you can go to this, they're on the README, so you can just copy and paste these out and try and see if we can figure out what we're talking about with each other here. Like I said, the slides are at that link as well, so if you want to, am I with the NSA? I am not. What am I trying to hide that I can't trust your government with? Well, it's right here, technically. Now, one of the things that's funny about having a name like James Alexander is that if you Google me, there's at least 1 million of us in Indiana. So if you say James R. Alexander, there's like 10,000 of us. So anonymity is really nice, being James Alexander. It's not like being Naomi Israel, I'm sorry, but it is nice to kind of be able to hide in a crowd. So as we've talked about throughout the day, Kevin Johnson mentioned at the top of the day that there are a lot of things when you're building an app that are actually required. You've got to make sure that you've got application level security, you're following OWASP top 10, even though he doesn't really like the way the 2017 numbers came out. Protecting against cross-site scripting, SQL injection, doing something in the SDLC itself, making sure that part of your process is evaluating whether or not this is something we can allow to be part of the application or not, is another level of security that you really have to consider. But none of that is actually relevant to this talk. I'm going to talk about this. I'm assuming all this top stuff is done, and it's perfectly implemented. We're going to talk about data encryption at rest. The overview of the talk, we're going to do a lot of definition of terms, and honestly, this is like a really small subset of what the actual scope of all the terms are in cryptography. I didn't want it to be even more boring a talk than it already is, so I'll give you a little bit of background, and then we can move on from there. I love the cast of characters that come along with cryptography. I'll just use Bob and Alice for my example here, but there's Carol, Dave, Eve, Mallory, Trent, and so forth that come into play as you get more and more protocols learned and more variations of scenarios. And then we'll talk about passwords and a little bit of AES encryption towards the end. So starting off, message that we're keeping secret, and that's the plain text. We've already heard that from a talk earlier. The ciphertext is what it looks like when it's encrypted, and we need to send it from somewhere and give it to someone else. So the basic formula would look like we have some kind of encryption function E, we encrypt our message, and it becomes a ciphertext. We can reverse it with the decryption, and so decrypting and encrypting ought to give us our message back from the original. A lot of cryptography is also being asked not just to keep a secret, but it's also being asked to authenticate that the sender of the message is who you think they are. Not only that, but that as the sender, you're sending it to a person that you think they are. So there's authentication in addition to just keeping the actual secret. Integrity makes sure that in transit, your data wasn't changed at all. And non-repudiation makes sure that as a receiver, I can verify that the sender has sent me something and that the sender can't deny later on that they didn't actually send me a message. I don't know if he actually invented the internet, but he really should stop dancing because his rhythm, doesn't always apply. Poor Al Gore. One of the things about cryptography is that for Kirchhoff's principle, we want to ensure that if it's a secure system, that everything about the algorithm is completely public except for the key. The problem with having a restricted algorithm is that if you have any kind of rotating number of users that are going to be using your algorithm, as soon as they leave your organization, as soon as they leave your application, they have the knowledge of what your algorithm was. So presumably, they can come back and either exploit that weakness or publish it to the world that, hey, they're using their own version of triple DES or whatever other cryptography in the NSA or in your organization. So the idea is that you want a fully public, fully recognized, academically approved version of whatever algorithm you're using to encrypt your data. Like the key mentioned here, it allows the cipher to be public while you have some kind of secret that you're maintaining. Imagine that a lock that you have just on your own key ring, but it's a digital key of some kind. There are two main broad categories. There's a symmetric algorithm, denoted here by my functions, where the key is the exact same for encrypting and decrypting your message. Examples of these are stream or block ciphers. AES is an example of this, where you can have a single key that will both encrypt and decrypt the message. An asymmetric algorithm uses different keys. So SSH, TLS, GPG, where you can encrypt with some kind of K1, your public key, and then only K2, some kind of private key, can decrypt the message that the sender was trying to send to you. From a cryptanalyst's perspective, we assume that an attacker has access to the communications between the sender and the receiver. We want to make sure that, even if someone, Eve in this case, the eavesdropper, is watching everything transmitting back and forth, the algorithm can still be considered secure even though they're monitoring all communications. The cryptanalyst can also know the full text, like I said, of the algorithm, and the goal is to find the key, the plain text, or both. So certain attacks, we have only seen the encrypted data, the ciphertext. Some number of messages, some number of plain texts, we need to either deduce the plain text from the ciphertext or the keys. Or we can find another algorithm that deduces the plain text from the ciphertext. Another option is known plain text or chosen plain text. So like a known plain text would be as if I told Calvin, hey, Calvin, go and tell someone else X, Y, and Z. I know he's going to say X, Y, and Z to someone else, so I just monitor his communication. However he ends up encrypting it, I can see that this message ends up being whatever it was encrypted to. So like an ambassador of a country or some other communication where you're relaying information and you can monitor that communication gives you information about the algorithm. Alternatively, you can actually choose the plain text and you can encrypt it yourself and give another data point on what the algorithm looks like. Probably my favorite algorithm is the rubber hose cryptanalysis. It's literally blackmailing or physical abuse or whatever means besides technology you can use to get the key out of somebody. Let's see. I talked about Kirchhoff's assumption. I talked about known plain text. In addition to like sending messages via ambassadors and such, HTTP has a lot of common headers that look very similar in plain text. So you'll know a lot of common text that's going to be encrypted over the wire. In terms of the breakage of an algorithm, we can say it's completely broken, where a cryptanalyst can, given any number of ciphertext, can get the plain text as a result. Global deduction gets, there is some other algorithm that you can get the same resulting plain text out, even though you don't know the exact algorithm used or the exact key used. Yet there's some other mechanism you can find to find the exact same plain text. And instance deduction is I can decrypt this one message, but I can't decrypt everything. And then information deduction is I can get some part of the key, a few bits of the key or the message, but not the whole thing. Data complexity here is the amount of data required that I have to analyze. So kind of hard disk space, but the amount of ciphertext I have to analyze. The work factor is how many CPUs do I need, how many processor time, how many CPU hours is it going to take, and then storage requirement of memory. How much memory is it going to take? Especially with memory hard algorithms, more recently, is a much bigger factor in breaking algorithms. An example cited often is if it takes 2 to the 128 brute force operations to break a given algorithm, and you have 1 billion processors, each performing 1 billion operations a second, it'll still take 10 to the 13th years in order to break it. So in the age of cloud computing, if you're having to resort to brute force calculations, you still want to make sure that the brute force complexity of your algorithm is 2 to the 28 operations. An operation typically is more than just, bit shifting or adding or multiplying or whatever. So the operations need to be sufficiently complex, and there needs to be a lot of them in order to fully explore the key space or the ciphertext space before you can say your algorithm is cryptographically or computationally secure, that it will take at least this long before someone could break it brute force. Given that the value of data decreases over time, this number is even more useful because, if you have something that's really old, like a 20-year-old block of ciphertext, the amount of effort someone's willing to go to and the amount of money willing to pay goes down over time. Remember to drink your Ovaltine. Yep, that's the first one. Steganography. For the longest time, I thought this was just a matter of concealing messages in images, but you can also use invisible inks or pin punctures. So if you've got messages written on pieces of paper, but then you puncture the paper in a given pattern, that could be some other message. So it's a way of concealing a message inside another message. Simple substitution ciphers like the ROT13, which is my crypto challenge. So it's the Caesar cipher, ROT13, is a simple cipher, an example of that. Homophonic uses a single letter code map to multiple letters. Polygram uses groups of letters, and polyalphabetic is multiple simple ciphers that are combined together for encrypting your message. There are very few in security, except for maybe if you're a Sith, and only a Sith deals in absolutes, which in itself is an absolute statement, so even Jedi can't use it. But one absolute we can say is that a one-time pad is perfectly secure. But there's an asterisk. There's always an asterisk, right? The key has to be generated from a truly random source of entropy. And truly random means that there is no way I can predict, given this key, what the next letter is going to be. So I wrote some Python to quickly do this, using a fixed key here to show as an example of why it's so hard, that given my ciphertext, if I know the key, I can get the exact message back one-time pad. However, some other key decrypts it to salmon eggs, and some other decrypts it to green fluid. So the same ciphertext with different keys could give you different messages. The trick is, though, a truly random source of data that is non-repeating. So you have to already have shared this private key with your receiver, which key exchange is really difficult as well. So, but we can say we do know that it is perfectly secure. So that's all more in like legacy text-based. Caesar cipher has been around for millennia now. Getting into more digital age, there's more sophisticated methods for encrypting bits. The XOR is really common. I'll show that a little bit later on AES. So I like to consider this one or the other, but not both, as an exclusive OR operation. And then here are a bunch of acronyms, a bunch of abbreviations. Password-based key derivation function, HAST, message authentication code, message digest, data encryption standard, and advanced encryption standard are all acronym soup. But PBKDF2 is I'll say the state of the art for password hashing today. It has the benefit of you just run it more iterations if you need to crank up your security on your given password hash. HMACs are used when you need to verify the identity and the authenticity or the integrity of a message. MD5 is a common message digest that is all but broken. That shouldn't be used anymore. The AES encryption standard AES was standardized by NIST in November 26th of 2001, which replaced DES and the arguably more secure triple DES. But now that we have AES, which is the underlying algorithm, we should just make a move to use AES everywhere. All right. That's a lot of text on the screen for a long, long time. Let's move on to building some kind of application. I assume who in the room, in general vague terms, is an application developer? You write code to make something happen. Who is a manager that is managing people but don't necessarily manage, don't actually write a code themselves? Who works for the NSA? Okay, that's good, because if we got to this point, I had to ask you to leave because we're supposed to be keeping secrets from the NSA. So a couple of features that we want in our app, we're going to have to do user login, and we have to store OAuth2 refresh tokens. The nature of this app is just really to hold the talk together. And these are two common use cases that I had to do recently, so I thought that it would be good. And specifically, I'm integrating with the QuickBooks Online OAuth2 token. And the entirety of the documentation, it just says encrypted refresh token, and use triple DES or AES. That's really all the more direction they give us. So I guess they assume that we're cryptography experts and we know what we're supposed to do with these tokens. So we'll see if Alice here can, and it looks like I have my slides out of order because the next one is not going to be in the right order. But so there should be a slide in here that says, I'm going to use a plaintext field to store my passwords in the database. And then Mr. Bossman comes in and says, hey, weren't you paying attention to the first slide? There's a whole lot of things that we need to secure it against. And even Kevin this morning mentioned, hey, there's a lot of things that are going to probably get our data out of our application. So if it's in plaintext, we've just given them everything. So we need to put a bit tighter controls over our own data. Until recently, there was a site called Plaintext Offenders that would actually shame publicly sites that use plaintext passwords. So if you received a plaintext password in your email, or if it would display your password in plaintext back to you, there'd be a screenshot on plaintextoffenders.com here showing of what the problem is. You gray it out or whatever, so you don't actually have your password. But we need a better option. Looks like we have some more questions here too. Let me see if I can read these. Random Easter egg, that's the second one, yep. Quantum computing change all the assumptions about cryptographic complexity and time to solve. Cryptographic complexity won't change, but quantum computing will change how many operations per second we can perform. So we'll just change the number of assumptions or change the number of calculations we can perform per second. And we'll have to increase the number of rounds we do or the number of, the amount of RAM we require, so we can just scale up our algorithms to scale accordingly. Do we need to store passwords anymore? What is your opinion on passwordless magic link logins? I like them a lot, and I've got a couple of options that I'm going to show later on too. I like the idea of getting away from passwords altogether. That we have a device or a token or a piece of software that will be our identity, and these HMACs that I just mentioned will be our identity. The trick then becomes, how do we secure that? How do we keep our phone secure? How do we keep that token secure enough that we can legitimately say, all right, that's me now, and I don't have to worry about losing it? One-time pads. By truly random, do you mean pseudo-random numbers are not true enough? Correct. So pseudo-random numbers are algorithmically generated from a computer. So you can get close by saying, all right, what are the clock ticks on my CPU? How much RAM am I using right now? All these other sources of entropy, but it's still at some point, like if it's a brand new boot of a machine that's launching 10 VMs, all those VMs are going to have roughly the same state. So your pseudo-random generator isn't going to be random enough, luckily. So truly random data, or like a ball hopper. So you've just got balls in a hopper, you pull them out, and you pull out a number. I've heard lava lamps are a good source of entropy. Anything they have like the audio port without a microphone connected gives you a lot of source of static, and so you really need to determine, is it a 0 or a 1? So that's what you need to determine, and however much entropy you can collect is how much randomness you get in your system. All right, that's a lot of questions. Route 13, we've already had people answering that the problem is here that it still basically looks like English text, even though it's encrypted or encoded or whatever. And Python makes it really easy. You just say route 13 and you rotate 13 characters over to get an encrypted version. The problem is obviously frequency analysis. The English language has way more E's and T's in it than any other letter. So our app dev, Bob, which has apparently been lost from my slides, he was going to have an appearance, says, okay, well, let's do Base64 encoding instead. And the problem with this is that it's pretty easily identifiable too. I think we've already seen answers where the double equal sign at the end is almost always a clear indicator. Hey, it's Base64 encoded. Base64 uses 6 bits for every 8 bytes to encrypt or encode. And then the equal signs are padding characters at the end to fill in the necessary bytes if they're doesn't encrypt fully equally. My first message that I would try to do for this slide was actually one that matched equally. So I didn't see an equal sign, so I had to change my message to actually have equal signs at the end of it. So a better option than Base64 encoding, because you can still get the message out of this, which is, for passwords, a horrible, horrible idea. You don't want to ever be able to get back to your passwords. So you need some kind of a hash. These are the 5 properties that a hash should have. The given text should always hash the same value. It can't be reversible. Any small change should have an appreciable change to the resulting ciphertext. And it should be infeasible to find 2 hashes that match the same value. Given recent attacks, as recently as February 23, 2017, Google and Centrum Informatica have the shattered attack. I hadn't heard about this until I did research, but they found an attack that was roughly 100,000 times faster than brute forcing SHA-1. Basically, the attack required the equivalent of over 6,500 years of single CPU computations and 110 years of single GPU computations. So it's still way better than the 2 to the 128th. So with the power of Google, they were able to find collision attacks in SHA-1 of 2 similar PDFs. There are now SHA-2 and SHA-3. We've mentioned SHA-256 here already, that are cryptographically secure enough for today plus, I'm going to say, 10 years or so. But tomorrow that may change. Google may drop a new attack on us that fundamentally changes the way we think about these things. So here are some examples. MD5, if I change a single bit of this string, the hash changes dramatically. With varying sizes of the digest of SHA, the message size increases, which is essentially the point of increasing the number of bits of output. And here's the example of 2 files that are varying only by 6 bits. Here's an easier way to see the exact bits that are different between these 2 files. So with these 2 files, if I hash them, I get the exact same value. Which is bad. You don't want your hashes to ever identify 2 things that are different as the same thing. There's a similar problem with PPKDF2 using an HMAC function as its hashing function. Here, SHA-1 indicates is the hashing function used, and the problem is that these passwords are so long that they're actually longer than the block size of SHA-1, and so it gets truncated for both of these cases, and they end up hashing as well here, and they collide, which again is really bad. You don't want if a user uses these as a password, you're going to have 2 different users that have the same password, even though they're very, very different passwords. The second parameter here after SHA-1 is the password. That's what I've got here in the commented section. So even with assault, even with 1,000 rounds, they still end up hashing to the same value. Does everybody remember the LinkedIn attack? Back in 2012, LinkedIn announced, I don't remember how many accounts were leaked, and they all used unsalted SHA-1 hashes for their password storage. Here's some stats from the time of how many hashes an ATI on Radeon can do 10.3 billion single-run MD5 hashes or 2.6 billion single-run SHA-1 hashes per second. So an attacker can just iterate through brute force as many of these hashes as he can, depending on how many GPUs he's got on his system. The second link here on the second bullet is from Robert Graham, and he goes through in great detail how to take the RockU database, the unsalted SHA-1s, and get back to plain text passwords for I think over 50% of the entire file with just the RockU database, which is a leak of plain text passwords from the now defunct site RockU that had plain text passwords in it. So given the combination of just what's in your word list, changing leet speak, adding combinations of words, you get over 50% brute forcing of the passwords. Here's a more modern day rig from last year of a video of guys building a machine that costs 5 figures and has 8 NVIDIA 1080 GPUs. If they're calculating Intel M hashes, they can generate 341 billion hashes per second. And I don't know of any password I can come up for Windows that can withstand an attack against 341 billion hashes per second. So I just kind of raise my hands and say, I give up. Here's my passwords. Save them the trouble. So all this to say is we need a better solution. I like the idea of tokens instead of passwords. Is that NVIDIA machine generating Bitcoin now? It really ought to be. I don't know what they're doing with it today, but this was from a video from February 2017. So in our application, we originally used MD5 in my fictitious application. So now we're going to use something called Argon-2. The Argon-2 hash protocol was it was released as the winner of the password hashing contest in 2015. They started the contest in 2012, and that was when they first announced that they wanted to have this contest to find the next password hashing algorithm. There's a consortium of, 24 different individuals that are way smarter than I am, academics, that study password hashing. And not only did they decide on Argon-2, but they found 4 other algorithms that had very specific properties. So memory hard problems or higher cyclomatic complexity that they allow them to learn way more about the problem of password hashing. As of January 2017, the Internet Engineering Task Force still recommends PBKDF2 instead of Argon-2. There was no mention at all of Argon-2. Personally, I think that's probably an oversight. Maybe they had specific reasons why they don't want to go to Argon-2. Maybe it's just too new, which is a problem in security. Things are too new. They haven't had the time to be rigorously by the academic community. So I suspect, at least in my personal use, I'm planning on using Argon-2. There's Django. If you install the Argon-2 CFFI library, you can add Django settings to say use Argon-2 as your default hashing algorithm, because I like the tunability of it that I'll show here in just a minute. But the problem with having MD5 passwords is that you can't get back to the plain text anymore. So you have to have some kind of rolling way of changing passwords. So the next time the user logs in, they're going to use Argon-2 instead of MD5, or you have to have everyone reset their passwords all at once. Neither one is a great idea, and it depends on the severity of the breach. So if someone just releases your password hash database, you probably want to just invalidate everybody's password right away. Versus if it's something you want to migrate to eventually, you can probably just wait for everyone to log in and then reset the ones that didn't log in a month's time or whatever. So here's what our MD5 hash looks like today. And then if we want to migrate to Argon-2, what the resulting hash would look like. We're using a library here called passlib that assigns this format for us. So with a $ here. And this would be your clue as you're migrating passwords from MD5 to Argon-2, you could say, all right, does it start with a $? If it does, then you know you've already migrated them, and you can just continue using Argon-2. If he hasn't, you have to go back to MD5 or whatever your previous hashing was. What I like about this is that there are these properties here, M, T, and P, that will allow you to tune up and down how hard the memory cost is, the number of rounds you run, or the parallelism that is required to actually hash this single hash. So this way, if next week someone finds a hack that reduces the complexity of finding a hash value, you can say, all right, let me tune up the memory, or let me tune up the degree of parallelism so that now requires 10 processors instead of just the one that I did before. There are a couple of different variants of Argon-2 as well. There's 2i that I mentioned here, but there's also 2d, and there's an I and D that combines the two. The I version uses data-independent memory access, which is preferred for password hashing and password-based key derivation. But it's slower and makes more passes over memory to protect trade-off attacks. So you kind of have to do a little bit of determination of which was more of your intent of protecting your passwords. How secure do you need to keep this data? Okay. So we already mentioned here in one of the questions that it would be nice if we didn't have to manage passwords at all. Just someone else do it, like Auth0. Auth0 does basically all of the work of maintaining the authentication for us. So instead of keeping username and passwords in our database, we can redirect to Auth0. We get a handshake back of this user has authenticated, and we let Auth0 do with the actual password storage and hashing all themselves. Benefits for the free option, even still, they can do up to 2 social identity providers. So if they want to log in with Google or Facebook or whatever, you get it for free from Auth0. You don't have to mess with it at all. Other passwordless options are, on the left here is Squirrel, SQRL, Secure, Quick, Reliable Login. And the FIDO Alliance is Fast Identity Online. Essentially, each of these are kind of the same product built by 2 different people, 2 different groups. But they provide some kind of a token that you say, all right, I'm going to log into Amazon.com. Amazon it would need some kind of server interaction as well. Amazon will present to you some kind of a token or a hash or whatever that you can click on, and then that goes to your device or a piece of software running on your machine that says, okay, looks like you're trying to log into Amazon. I say, yep, I'm logging into Amazon. And then that token goes back to Amazon to identify you as the user so that there's really been no handshake of passwords, yet your device or your software has an HMAC that is cryptographically secure, identifies you, but you didn't have to log in, didn't need a password, didn't need any of the overhead of the hashing. Okay, moving on from hashes, we need to store our OAuth2 tokens for QuickBooks Online. We have the benefit of the algorithm, or the third party, says that refresh tokens will only be valid for up to 100 days, and as soon as you ask for a new token, the old one expires after 24 hours. So the length of time that we have to keep our data secure is at most 100 days, and after that, the token is invalidated by our third party. So we have a little bit of a break in terms of it doesn't have to actually be secure from the NSA, although given the title of my talk, it would be nice. Pythology NSA Twitter account now. Is there? That didn't take long. All right. I mentioned AES before. This is a subset. AES is an instance of Rindall. Rindall specifies any multiple of 32 bits, block sizes and key sizes, with a number of rounds, and essentially you hash and XOR and bit shift and do byte lookups into a lookup table that allows you to encrypt whatever block size with any key size that you want. AES standardizes on 128-bit blocks with key sizes of 128, 192, or 256. So if someone says Rindall, they're talking about AES, but AES happens to be a specific number of bits of Rindall. And Rindall was developed by these 2 Belgian names, Vincent Reimann and Joan Diamond, I'm going to say. But I Probably should have looked up the pronunciations better before the talk. Here's a quick video that I'm playing on the wrong screen that will give an example of how the actual algorithm works. I did not make the video or the flash animation that's involved here, but the idea is that you get plain text in, you get a key in, and then it's going to go through a number of rounds that we're going to show here any second now, I promise. So here we are. So we take our key, and based on the size of the key, oh, that's great. Let's get rid of that. Based on the size of your key, you're going to do some number of rounds. 120, you're going to do 10. 192, you're going to do 12, and 256, you're going to do 14 rounds of substituting a number of bytes, shifting your rows, mixing your columns, and adding a round key. So this is doing multiple things on each round to encrypt your plain text. I will note that at 2 minutes 30 seconds, there is a slight XOR error. Is that going again? Yeah, that's going again. By 2006, the best known attacks were only on 7 rounds of 128-bit AES. So part of the attacking of AES involves, let's not do 10. Let's see if we can break it at 7 rounds or 5 rounds or whatever. And I think as we saw during one of our lightning talks, a bigger vulnerability for AES is side channel attacks. Cache timing attacks and how long it takes to do these lookups and do these mixing of columns and so forth, that actually provide a bigger weakness than the actual algorithm itself. So you're exploiting the way computers work versus the way the algorithm works. For reference, the NSA requires at least a 128-bit key for secret information, and if you need to store top secret information, you need a 192 or 256-bit key. The length of the key requires more rounds and is more difficult to break cryptographically, so that's why it's probably the top secret. I think top secret also has a expectation that needs to be secret for at least 50 years or 60 years or whatever. In our case, 100 days is way less than that. Here is some Python code that implements the Fairnet cipher. Fairnet is built on top of AES. This code is straight out of the cryptography library, so I'm really just stealing it here. But as you can see, we really just include Fairnet, generate some key, and this is the part that you need to keep safe. Store it somewhere other besides here in line in code. And then given your key, give me some text to encrypt, and now I have this token. I can decrypt it later if I need to. If I want to have a byte array or a URL safe version of it, I can get to that pretty easily as well. An interesting quality of this, if you look at the first few characters here, and all of these, it's ga, so clearly there's some pattern to this. The spec has the Fairnet chunk broken up like this. So the beginning is always some version number. There's a timestamp, initialization vector, ciphertext, initialization vector I didn't mention before, but that is often used commonly in cryptography as well. It's funny, when I was researching Fairnet specifically, Chad Whitaker was looking at the spec and saying, what's going on with these leading bits? Why is this GA in every single one of them? And why is the version always the same, even though there have been 10 revisions to the spec since it was released? Then you just see him chatting with himself in the Git repository, in the Git issue, answering his own questions. There's been no response from the maintainer, but he answers his own questions. So thank you to Chad for helping me guide some decisions here. But at the end of the day, Fairnet just wraps around AES by adding the IV and the version and so forth. So it's really nothing new. It's just a different implementation on top of AES that's built into Python for us. If you want to make your ciphertext even harder to decrypt, you can use a PPKDF2 on top of it. So you can come into the hazmat section of cryptography, which I think is aptly named, because if you're getting into hazmat, you need to be sure that you know what you're doing. Again, this comes straight out of the documentation. But the critical parts here are using OSU random. So that's the operating system's source of randomness. In Unix systems, that'll be dev random, and on Windows, it'll be the API call for getting random bits back. So you need a random salt, however many bits you want of it. The iterations here I've increased from the documentation. The documentation mentions 100,000, and that was back for 2014. I assume it's been 4 years. We've come a long way in that amount of time, and my data is really important, right? I want to make sure it's got as many iterations on it as I can. And if my company is small enough, I only supporting a company of 15 people, so I can crank up the number of iterations here, and it's no big deal. If you're hosting a server that's got a lot of logins simultaneously, you might consider tuning these numbers to say, all right, maybe I don't need quite as many because it'll just be that much heavier on your servers. So in conclusion, cryptography is hard. The math, the background, all the academics involved with finding the algorithm, tuning it, making sure it works, is really, really difficult. But it's also the easy part of maintaining an application securely. Cross-site scripting, SQL injection. There's a whole host of things that are really easy to mess up when you're deploying an application. When someone says, I need cryptography to help me secure my website, you're really saying, you don't know how to secure your website, because there are a lot of other things you have to do probably before you go to cryptography just to secure your website. The benefit of crypto is that it's got a very well-bounded box of what you're securing, what your inputs are going to be, and what the cryptography is expected to do. Some additional reading, if you want to go more in depth to this, a lot of my slides came from the book on the left here. The book on the right is by the same guy, and it was written in 2010. So he took what he wrote, Bruce wrote both of these books, and he calls applied cryptography like the theory behind cryptography, and then the engineering book is more what you can actually do to implement things in your day-to-day application development. I don't see any more questions coming up, so if you're so inclined and you want to download my Jupyter Notebook, I've got one final challenge for you there at the end that I didn't bother making a bit.ly link for, so I apologize. So thank you very much.
Excellent. Well, let's give James a big round of applause. Thank you very much.